Exponential growth and decay has to do with things growing quickly, as in biology problems. If you put bacteria in a dish, if your stocks grow exponentially, that's a good thing. If your business grows exponentially, that's a good thing. So if something is growing exponentially, it goes up, what happened? It goes up kind of fast, right? So if you have an exponential growth, it kind of goes like that. And if you have something that's exponential decay, it kind of looks like that. And it goes down and approaches an asymptote. Here you start from an asymptote and go up. Here you start from way up high and then you go down, okay? But usually you don't actually start from infinity. You actually start at a point and kind of go down. Hello.
No.
Do I have a protractor? No, I haven't. I haven't had a protractor. Do you know so if this so according to this number a sub 0, that's the initial amount. That's the amount that you start with, or the number in your initial sample. So you might start with like the population of the world, and some people believe that there was only 2 people who started, right? And then that grew up exponentially to everyone that we have now. How about that? Okay, or you can start with 1 bacteria and grow exponentially. So if this is a number, if k is a number bigger than 0, then it's going uphill like this. And if k is a number less than 0, meaning a negative number, then it's going downhill. Okay? So a colony of bacteria, according to the law of thermodynamic growth, that means it goes up, keeps growing forever without any limits on the top. And you have this equation. What is the initial amount of bacteria? And all you have to do is look right here, and that's the initial amount, 100. Okay? So the answer to that is 100. And the other way you can figure that out is at the very beginning, t is 0, right? So the initial amount is t is 0, and this gives you e to the 0, and anything raised to the 0 is what? 1, and 1 times 100 would give you out 100, all right? And then what is the growth rate? And that's the little number right here, okay? So it's 0.045 or 4.5% or 0.045. Okay? And so it's growing 4.5% per day, right? Graph the function on a calculator. We can do that. All right, so the way you do that is you get your calculator and you go y equals clear, y equals 100. E is above the natural log key, not coincidentally. 0.045. In this case, x is x. You know, say why can't you put a t there? That's the t is for when we get to parametric equations. So your variable, you still have to call it x. All right. And then you kind of got to be kind of smart about the window. Okay. And so in this case, it's growing 4.5% a year, and or a day, sorry, and you start at 100, right? So if you when you're setting up your calculator window, you gotta set it up so that, because a lot of people come up and they say, my graphing calculator isn't working, and that's because you're not thinking about what your window should be. So let's just guess, I don't know, maybe 100 days out, you want to see what's happening. But your y-min, you could set that at 0 because it's never going to be negative, right? But your y-max, since you're starting, your initial is 100, you would think you would want to go a lot higher than 100, right? So maybe set that, I don't know, make a guess. What do you guys want to guess? Let's set that to 500, okay? So that's a good guess, and let's hit graph and see what we get, okay? So that looks pretty good, and so you can see that That's your curve, and it starts at 100. I don't know what this is over here. Second stat plot. Plot off. I'm going to turn that up. Okay. So, graph. So you can see this little graph that goes like that. The next question asks you, what is, we did that. What is the population after 5 days? So an easy way to do that is on the graph. There's a couple different ways to do it. But one way you can do it is second calculate value. Second calculate value. And you just plug in 5 in there. It should give you out the answer, right? And so after 5 days, the population is 125.23. Okay? So I need to write that. 125.23 bacteria. How long will it take for the population to reach 140? Well, that's, you want to figure out what x is when y is 140, right? And so what you have to do, probably the best way is to do that. You can do it with logarithms. We'll do the next one with logarithms. But we'll just do this graphically with your calculator. So I'm going to come over here to y equals 140 and plug it in there and hit graph. And then I want to find the point of intersection between those two, which you could do second calc, intersect, which is 5. And they'll say first curve, since you only have 2 curves, you can just hit enter. And they'll say second curve, you hit enter. And since there's only one place where they cross, you could just hit enter again. If there were 2 places, then you'd have to get kind of close to where they cross. But in this case, it just goes right to there. And so about 7.5 days. Yes? Easy? Yes, sir.
Wouldn't part B just be like 125 because it doesn't like have a fraction of bacteria?
I think, I don't know.
It can be, well,
I don't know how
they could be
bacteria
split
would
as, so.
Yeah, maybe they're splitting.
Yeah.
But
Yeah.
it's either one bacteria or
No, it's either one bacteria or it's turning into this.
I once dated a bacteria,
Biology.
but she split.
I appreciate it.
What did you just say?
I said I once dated a bacteria,
Oh, you told
but
us this.
she split. Yeah. Okay.
I wonder why.
I don't know. She was an amoeba, actually. All right. Anyway, I just made that one up. What is the doubling? What is the doubling time for the population? So the way you could set up this is like 2p equals the beginning p, right? And it doesn't matter, or you can put like 200 here. Actually, I guess what you should do is put like 200 here equals 100 e to the 0.045 t. And then you divide both sides like that, and you get, this is a lot like how long will it take your money to double, right? 0.45 t. And how do I solve that? Yeah, you could take the natural, you could solve that with your calculator, but it'd be kind of better to do this one with your logarithm. So if I take the natural log of both sides, right, I get that the natural log of 2 equals, or when I take the natural log of e, you just get 0.045 t. And so then you get that t is equal to natural log of 2 divided by 0.045, which is about equal to something. Equal to 15.4 days. About 15.4 days. Easy so far? Have you done this before? Maybe? Yes? No? Okay. Only 4 questions. Yeah, only 4. I'm actually going to add 1 to your homework, so don't get too Don't get too complacent. Yes. All right. So the next thing, where's the next problem? This one? Is this the next problem? So here's another colony of bacteria increasing according to the law of uninhibited growth. If the number of bacteria doubles in 3 hours, write the function that gives the number of cells in the culture. Okay? So with this one, what you want to do, so in this type of problem, you have to find the constant first. All right? So what I'm going to say is it doesn't matter how much you start with, okay? But you have 3 times the amount e to the k. Do you understand where I got? You could put like a 1 here. Whatever, it doesn't matter what you put here and here, just as long as the ratio of this to this is 3, right? And it doubles in 3 hours. Yes? Okay? So then solving this, that you could do that the natural log of 3 equals 3 times k. Any questions so far? And then I find k equals, whoops, doubles, not triples, I'm sorry. That should be doubling in 3 hours. And so that should be natural log of 2 equals, so 3k. So k is equal to natural log of 2 divided by 3. Now if you're doing this on your calculator, which you'll probably do, what you want to do is leave it in your calculator. Okay, so you want to store it in there. So k, I'm going to go natural log of 2 divided by 3, and I want to stow that as, just call it alpha. You hit the stow key, you go to the stub. You go to the stub, and you get some, and you stow it as alpha, and then you pick a letter that you want to stow it as. Okay? So I'm going to stow it as alpha A. And don't forget to hit enter, which I forgot to do in the last class. Hit enter. So now that value for k is stored in for A in your memory. Okay? Now how long will it take for the size of the colony to triple? So then you could write an equation like this. 3 equals e to the k times t. Well, we know what k is, right? You understand that? Good? And so you put a 3, you take the natural log of both sides. Natural log of 3 equals kt. So t would be the natural log of 3 divided by k. And so then what's nice in your calculator, now there's no rounding mess ups or anything like that. You just go natural log of 3 divided by, and you go alpha A, and it will just plug that constant right in there so you don't have to keep plugging in and rounding it up. And you get about 4.75, days, hours? Hours. Okay? So that's some fast growing bacteria, right? Questions on that? We're good? Are we still recording? We are. All right. So now we're going to go to the next thing. Go away. Which has to do with radioactive dating, right? So radioactive dating, it's kind of the same formula. It's some. What? Yeah, you can. I was trying to come up with a joke that I goes radioactive dating. You know, I can't think of something.
My girlfriend's an atomic bomb.
Oh, my girlfriend is an atomic bomb, so we're doing radioactive dating. That would be pretty good. I don't know. Okay. That was pretty good. Anyway, so if the half-life of carbon-14 is 5,600 years, approximate when was the tree cut and burned. So the trace of carbon, so this is how they figure out how old very old things are, because it has 1.67% of the original amount of carbon. And I don't know how they know how much it originally had. I guess comparing it to a new wood that's alive, you can figure out how old something is. So what a half-life is, it's how long it takes for something to decay down to half of its original amount. You know that?
Yeah.
So the way you set this one up, you can say that 1/2 of A is equal to A e to the k times 5,600. See? And then the a's go away, right? Because you have half the amount after 5,600 years. And now you can take the log of both sides. Ln of 1/2 equals 5,600k, and then you can solve for k. So k is equal to natural log of 1/2 divided by 5,600. So you're going to do that and put it in your calculator. Ln of 0.5 divided by, yeah, it's a small number, divided by 5,600, and you get this very small number. It's a negative number because it's going downhill, right? So that's negative 1.203 times 10 to the negative 4. So it's like negative 0.000123, right? So, and then you want to stow that as well. Stow it, and I'm going to stow that as alpha b, okay, for that constant. And now it's in my calculator. So now it says, can I make this smaller? View, edit, tools,
What, the calculator?
yeah.
Grab the one.
No, it doesn't work that way. Never mind. I don't want to mess something else for you. Just fine. Wait. Oh, size. We want it smaller. This is, let's go for, ooh. That's too big, size. I guess we're using a small emulator. That's pretty, it won't let me shrink it. Will it? Nah, it doesn't. Anyway, let's try a small emulator. Okay, that just, now it's bigger. I don't know. All right. So anyway, using a graphing calculator. So we haven't answered the question yet. Okay. So now what you want to do is, now you have your constant, and this is the amount left. So what you know is that you have 0.0167. Did it say graphic? It doesn't say graphic, does it? Does it say graphic? No. 0.0167 equals e raised to the 5,600. No, that's wrong. E raised to the kt, right? And so you want to solve this because it says, when was the tree cut and burned? So what you want to do is solve this for t. I'm still answering this question, then I'll graph it, okay? So I take the natural log of both sides. Natural log of 0.0167 equals kt. So t is this divided by k. So again, I'm going to go natural log of 0.0167 divided by alpha b, right? Alpha b. And I get 33,062 years. Okay? 33,062 years. So that's a long time. Okay, 0.44. So, so that's why, you know, they talk about nuclear waste and stuff like that. That's why you don't want to have nuclear waste, because it takes a long time to get rid of, right? Because this is until it has 1.67% of the original. So that's how long it might take. If you want to graph that, do you want me to graph that, or can you do that? You can graph it. The only thing you have to be careful of on your graph, determine the time that until half of the carbon remains. Well, we already did that, didn't we? Right here, right? 5,600, guys. And then the only thing that you have to be careful of when you graph it is that you set up a window that's sufficiently big. Because as you can see, let's do this, okay? So when I'm setting this up on my graphing calculator, when I go into my y equals, so I have, you want to graph this relationship, y equals e to the kt, and so there's nothing in front, because all you're graphing is the percent remaining. So this divided by this will give you the percent remaining. You see that? This divided by this as a decimal. And so all I have to graph is second e raised to the alpha b times t, okay? Which in this case is x. But when you set up your window, well, it took me a very long time to get down to 1.6%. So I'm going to set my window not to x max of 100, but to like 50,000 years, okay? Because you understand why it's got to be so big, okay? And
Wait, what was the equation?
it was like negative 0.0001 something.
Where did you get that from?
I got it from over here, taking the natural log of 0.5 over 5,600.
Oh, so that number.
Yeah, that's enough. Okay, so I'm going to set my window really, really big. And then I'm going to set my y max, okay? Since this is a percent as a decimal, and the highest percent you could have is what? 100 is 100%. So 100% as a decimal is just 1. So I'm setting my y window from 0 to 1. And then if I hit graph and cross my fingers, I get this graph of exponential decay, where this is the percent of the sample left at time 0. So at time 0 you have 100%, right? And then as time goes on, you would have nothing. And then how long until half of the sample remains? Well, you could do something like plug in down here 0.5, and if you hit graph there, you can see where those two cross. And again, if you go second calculate, and I hit intersect, I know I'm going kind of fast, but I want to get to the last thing. Intersect, I hit enter, first curve, second curve, guess. Notice that half of the sample is left. Yes?
You had the wrong one.
I had the wrong line.
Yeah.
Oh. What did I do wrong? Oh,
left
yeah. I don't need this line, right? This line I could delete. Delete. Something was wrong. Clear. Okay? So now, graph. And there's the first curve, second curve, and I'll say second calc, intersect 5, and first curve, enter, second curve, enter, yes, there. And notice that you have half the sample remaining at 5,600, which means my equation must be correct. Yeah?
Yes.
Okay. All right. Moving on to the next thing. Sorry to go so quick, but we gotta go. The next thing is called logistic growth. Okay. And have you guys seen this before? Hey, can you stop talking? Thanks. All right. So I won't say your name to the viewing audience, you know, but they know who you are. Okay. So, hey, wait. Anyway, so a logistic model, it's a more realistic model because if you have, most things don't grow exponentially. Well, that's kind of a fat mind. But most things kind of grow, they start off growing very kind of slow, and then they start growing faster and faster and faster. Like the population of Louisville. Like when I was in college here, there weren't very many people in Louisville, but then it grew really, really fast, like from the 80s, 90s and stuff like that. And then what happens is you hit kind of a saturation point, right? Because they say, oh, we can't build any more houses, or no one's going to have anywhere else to live, right? Kind of with the planet and stuff like that, or bacteria, or whatever it is. And so what happens is, after a while, things kind of level off, and you approach an asymptote. So you start with an asymptote down here, but with logistic growth, you kind of start here, right? Because time is equal to 0, and you might increase really fast, and then you approach some saturation point, okay? And this number up here, the top number is called the carrying capacity, okay? So so in this is the function, okay? This is the initial amount, usually right there, okay? This is the growth rate up there. This is time. This is the carrying capacity. So this is kind of like this asymptote up here. So in this case, what is B? B is the growth rate, okay?
What is A?
A is the initial amount, okay? So state the carrying capacity, that's 230, what are they? Fruit flies. Flies, yeah, okay? Flies, and the growth rate is 37.37, negative. Net was 0.37, or 37% per
Why is it
population after T days, right? And so determine the initial population. So the initial population, if I plug in 0 in here, we could just kind of do this algebraically. That's when time is equal to 0, right? And so 56.5, what happens here, this becomes e to the 0. What's e to the 0? 1. And so you get 50, so what you end up getting, 230 over 1 plus 56.5. Do you guys understand that? Which is 230 over 57.5, which comes out to be 4. Okay? So what you started with is 4 fruit flies.
I
0.
thought A was the starting.
I
Oh,
did say A was.
Yeah, you said A was
oh, I
the
did say A
starting.
was the starting amount. What is A?
That's a bit of a conflict.
I guess it's just some constant.
It's
Okay?
ambiguous.
So I'm not exactly sure. It is some constant that I guess has to come up out of the formula. Okay? So, but anyway, the original amount is 4. Okay? Graph P and T. This is kind of tricky to plug into your calculator. Do you want me to try and do that? Okay, let's see if I can do it without messing up. All right, so y equals clear, and go up here, 230 divided by, and I would put this mess in parentheses, 1 plus 56.5 raised to, and what I would do just to be sure, now the little box is up there, so you're okay. Negative 0.37.
Wait, what about the E?
Whoops, I forgot about E. Oh, let's get picky, why don't we? 56.5. Yeah, Logan. 56.5. Insert second E raised to the negative 0.37 x, and then I'm gonna close. Do I have anything after that? Delete that. Okay. Delete. Delete. Okay, and then I think I could just put a close parentheses there. And then you want to make sure that your window makes sense, okay? And so since I know that I start with 4 and the fruit fly goes up to 230, I'm going to go window from 0. I probably don't need to put in 50,000 there. Maybe I'll just put in 10, see what happens after 10 days. And I'm going to say my Y max to 230. And I'm going to cross my fingers. And I'm going to hit graph and see what I get. So it looks like it's going up. I think I want to change, put in more days there, right? Don't I? So I'm going to make my days longer. So I'm going to put in 100 days and see what happens. And you can see that I probably want to go higher than 230, but you can see the logistic growth curve. And then it says, what is the population after 5 days? Second calc value, and you just plug in 5, and you will get that answer, which is 23.27 fruit flies. I guess you can't have 0.27 fruit flies, but getting pretty close. Rapid, we did that. And then what else did we miss? What's the last question ask you? How'd that get so big? Go away. The last question asks, hello. It's a huge thing. Go away. Okay. And the last question asks you, how long does it take for the population to reach 1/2? Or how long does it take? So 180, we would graph the line 180 and see where it intersects, y equals. Graph the line 135 and see where it intersects. And then you're going to do 334, 149, 21, and one more.
No.
27. I'm adding that. Okay? So, because I don't think I had a logistic growth one in there. Did I? I don't know. Okay, and that was a lot of teaching today, so thank you. Sorry it's so long.